Okay, so this first part goes back to what we did all the way in the beginning. I'm going to go kind of fast through that beginning stuff because I'm assuming we need to spend a decent amount of time on halogenation mechanism. So start with this stuff. The first thing I learned was about methane. It's the simplest organic molecule. Right, it has one carbon surrounded by 4 hydrogens. Okay, so carbon is tetravalent, which is very important. So it always needs 4 bonds to be stable. Okay. And methane has a tetrahedral shape, and all these bonds are sp3 hybridized. And then tetrahedral carbon always has 2 bonds that are in the same plane. So if you look here, I have 2 bonds that are flat against my hand in the same plane, then I have one in the front, one in the back. Okay, and that's true for all carbons with 4 bonds. Okay, and this wedge shows that this hydrogen is in the front of the plane, the dotted lines are in the back, and then straight lines are in the plane. Okay, so these CH bonds are formed by hat-to-hat overlap of this carbon's sp3 orbital and this hydrogen's 1s orbital. Okay, so that's how all these bonds are formed. And then carbon-to-carbon bonds are formed by sp3 to sp3 orbital overlap. Any questions there? Okay. So there's a few different ways to show organic compounds that we learned. So this pentane, right? And then hexane, heptane. So these are 3D structures that shows you where things are in 3D space. It shows you what's coplanar, what's in the front, what's in the back. So in this example here, this whole line is in one plane, so that you can imagine that it's just flat on the screen. And then all the wedges are in front, dotted lines are in the back. Okay, so as you can imagine, once you get big molecules, this is pretty inconvenient to draw. So we can have structural formula, which drops out what's in the front and the back and just shows what is connected to what. Okay, and also, as you can imagine, once you get big molecules, this is also pretty inconvenient. So what you'll see most of the time is condensed structural formula, where we just group a carbon and its hydrogens and just write it like that. So this carbon has 3 hydrogens, we write it as CH3, CH2, 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 and then CH3. The same thing for all these. Okay? And if we want to get even simpler, we can use line structure. And line structure is where points like these represent carbons, and the lines represent carbon-to-carbon bond. Okay? And we know that all carbons have to have 4 bonds to be stable. So for example, this carbon here only has 2 bonds shown, but it's assumed that all the bonds not shown are to hydrogen, just for shorthand's sake. So this carbon only has 1 bond shown, so we can assume that the other 3 bonds are hydrogen. And this is 2 hydrogens, 2, 2, and 3. Questions there? Okay. So, class of organic compounds. We have alkanes, okay, and this ANE tells us that all the CC bonds are single bonds, which we also call sigma bonds, okay, which are that hat-to-hat overlap. Okay, and the formula for molecular formula for alkanes is generally CnH2n plus 2. So if you're going to see a compound with that molecular formula, you can know that it's an alkane, that there's all single bonds. Okay, and it's just a number of carbon atoms. Okay, so these are all your prefixes for the number of carbons you have. You're only expected to memorize up to 8. They're not hard to memorize. Probably already know them by now. You have methane, ethane, propane, butane, pentane, hexane, heptane, up to octane. Okay, so alkyl groups are formed by removing a hydrogen from an alkane. You know, typically see this represented by R. So you would see like, get my pen. So you might see something like this with an R, and that would just tell you that there's some alkyl group there, some undefined carbon thing. So same prefixes as alkanes. When you have one carbon, it's methyl, but you're just going to drop the ANE and add YL to show that it's an incomplete group. So you have methyl and ethyl. Okay, and this carbon only has 3 bonds, so it's unstable, it's incomplete, needs to be connected to something else. Okay, so once we get up to propyl, 3 carbons, we have a few options of where our incomplete carbon could be. Because we could take a hydrogen from terminal carbon, okay, which would give us N-propyl, normal propyl, or we can take a hydrogen from this middle carbon, right? And we can have the incomplete carbon in the middle, which would give us isopropyl. Yeah, that sounds familiar, right? Isopropyl alcohol. So same thing with 4 carbons. You can either take a hydrogen from the terminal carbon, have N-butyl. If you take a hydrogen from the second carbon, you'll have secondary butyl. Okay. Then you can take a hydrogen from this carbon, but move a methyl group here, and this is isobutyl. Or you can have the tertiary carbon be incomplete and then have the methyl group surrounding it. Okay, this is called tertiary butyl. And these names are coming from the classification of different types of carbons. So primary carbon, it's only connected to one other carbon, like this one here. It's connected to 3 hydrogens, 1 carbon. You have secondary carbons, like this one here is secondary, it's connected to 2 hydrogens, 2 carbons, and then tertiary, like this here, is connected to 3 other carbons. That's why it's called tertiary butyl. Okay, so then we talked about naming alkanes. So I have a few examples here we can go over. So your first step in naming alkanes is to find your longest carbon chain, and that's going to be your parent compound. Okay, so looking at this, you might be tempted to just pick the straight one, but that's not always the case on which one's the longest. So if we were to do that, we would have 1, 2, 3, 4, 5, 6 carbons. Okay, but if I start counting from this corner down here, I'd have 1, 2, 3, 4, 5, 6, 7 carbons. So this here is actually going to be my parent compound. Okay, and my parent compound has 7 carbons long, so what's my parent compound? Heptane, right. Okay, so now we need to number the chain. Okay, and we're going to number closest to the first side group. Okay, so I only have one side group. It's right here. So I'm going to start counting from that right side to give that side group the lowest number. It's going to have 1, 2, 3, 4, 5, 6, 7. Okay, so I need to name and assign positions to all the side groups. So what's my side group here? Mm-hmm. So this is a methyl group, and it's on carbon 3. So this is going to be 3-methyl heptane. Okay. And remember, you separate numbers from numbers with commas and numbers from words with dashes. Okay. Any questions there? Okay. So one more of those. It's a little harder, but not too bad. So again, your first step is to find your longest carbon chain. And again, you might be tempted to just pick the straight one, and sometimes it may be the straight one, but you've always got to double check to make sure there's not a longer one. So if I go with the straight one, it would be 1, 2, 3, 4, 5, 6. Okay, but I have to try all my options. So what if I try from this side and go 1, 2, 3, 4, 5, 6, still 6. But if I try from up here, I'd have 1, 2, 3, 4, 5, 6, 7. Okay. Or I could go 1, 2, 3, 4, 5, 6, 7. It would give you the same compound regardless. So this is going to be my parent chain. Okay, and it's 7 carbon long, so it's going to be heptane again. Okay, so now I need to number on the side closest to the first side group, okay, which should be on the right. Side group here, here, and here. So that right side is closer. So it's going to be 1, 2, 3, 4, 5, 6, 7. Okay, so now I need to name these side groups. So what's this first one? It's a methyl group. Okay, this one should be fluoro. Did I spell that right? Yeah. Okay, and then this one should be ethyl, right? Okay, so yeah, this one's on 2, 3, 4. So I'm going to start with which one goes first in the alphabet? Yes. So this is going to be 4 ethyl. Then what? 3 fluoro. And 2 methyl heptane. Okay. Makes sense? All right. So isomers, when you have the same molecular formula, but they have different connectivity. Okay, and these are called structural isomers or constitutional isomers. So this is why after propane, if it's just a straight chain alkane, you need to have an N in front of it to show that it's normal and alkane, straight chain alkane, not branched. So I have another example of this. I think you have to do something like this on your homework. So final isomers of C4H9Cl. So as you can see, this is a derivative of butane. Okay, so this still follows CnH2n plus 2, but I replaced a hydrogen with a chlorine, but it still is an alkane. Okay, so when you do these types of problems, there's not a like set formula on how many isomers there should be or how to do this, but what I would normally do is just start with a straight chain and then work your way past that. So probably the simplest one I can do is just my 4 carbons in a line, chlorine on the terminal carbon, and then fill in my hydrogens. Okay, so I have 4 carbons, 9 hydrogens, 1 chlorine. Okay, so what should this be named? So this is 1-chlorobutane. All right, because I have 4 carbons and then a chloro group on C1. Okay. So then next what I would do is try to move this chlorine around still on the 4 carbon chain. So I can put it on C2. Still fill in hydrogens. Okay, so that's still 3, 3, 9 hydrogens, 4 carbons, 1 chlorine. Okay. So that should be 2-chlorobutane. Okay. And I can't move this chlorine anywhere else because if I move it to the third one, it would be the same as this one. If I move it over here, it would be the same as this one. That makes sense? Okay. So now I can move on to the 3 carbon chain derivatives. Okay. So if I have 3 carbons here, I can put another carbon there, and then I have a few options where I can put my chlorine. So I'm going to start with chlorine there. Okay. And again, fill in your hydrogens. Okay. So I have 4 carbons, 1 chlorine, and 3, 3, 9 hydrogens. So what should this one be named? Be 1 chloro, 2 methyl propane. Right, because I have a 3 carbon chain here. So C1 chlorine and C2 methyl. Running out of room here. So my next option, what else can I do? Yeah, so if I move this chlorine over here, is that what you're saying? In the middle? Yeah. There you go. Right. So I can have methyl groups on all 3 sides, and then I can also put that chlorine connected to C2. And that should just be 2 chloro, 2 methyl propane. Okay. And I don't have any other options, so I can't move anything anywhere else that would give me a different compound. Okay, so I have 4 structural isomers. Okay, and like I said, there's not a set way to do this. There's not a way to tell how many isomers there will be. Sometimes the question will tell you, sometimes not. So just be sure to go back and check if you can make more, move things around, try things out, see if they make the same compounds or not. Any questions on that one? Okay, so briefly touch on this, but learn about cycloalkanes, okay, which is just when you have a ring, they're all single bonds. Okay, so bond angles will affect the stability of cycloalkanes. Okay, and this is just based on geometry, like we talked about in class. Triangle, these internal angles will be too small because carbon's tetrahedral wants to be 109.5. These would be too small. Same thing here, be like 90 degrees, be unstable because it's too tight of a bond. So cyclopentane, this internal angle should be 108, which is close enough to 109 that this is pretty stable on its own. And then cyclohexane, this internal angle should be 120, okay, which is a little too big. So this is cyclopentane. Hold on. What am I made? Okay, so cyclohexane, if it were to just exist like this, it would be unstable, okay, because these bonds are too wide. So what it does, it's called puckering, or I kind of think of it like crumpling a piece of paper. So you can either have boat conformation, where, see, if this was flat, then these two end ones bend up to have boat conformation, or you can have chair, where this one is up and this one is down. It looks like a chair. So like 99% of all cyclohexane is in chair conformation. It's just more stable because these are farther apart. But yeah, any questions there? Okay, what you've all been waiting for. So this is our first mechanism that we went over, called radical halogenation. Okay, so halogenation is just telling you that we're putting a halogen on alkane, and we'll only ever use bromine and chlorine. And then radical is telling you it takes place via radicals. So a radical, remember, is just something with an unpaired electron, which means it's unstable, it's energetic, it's going to attack things. Okay, so for this reaction to occur, we need our alkane to be in excess, okay, for mono substitution. So if we just want to put one halo group on your alkyl or your alkane, you need the alkane in excess. Okay? And this will only happen if you shine light or heat up the reaction. So this H nu here is telling you that there's light. Okay? It's a 3-step reaction here. This first step is initiation, and then these 2 steps here collectively are propagation. So we can go over this mechanism, and I also have an example after this, but okay. So this is cyclopentane, right? Okay, and then I have molecular bromine. I'm going to shine light, and then my product is I'm going to replace 1 hydrogen on this ring with a bromine. Okay, and then that hydrogen will combine with the other bromine to form HBr. Okay, so this first step in the mechanism is called initiation. Okay, and this is what we need light for. And these dots are a little wonky, but so I have molecular bromine here. Okay, this has 3 lone pairs of electrons. I don't know why the dots aren't showing up. I'll fix that. Okay, so 3 lone pairs of electrons each. You don't need to show that. Okay, and then this bond here has 2 electrons in it. Okay, so this bond is going to break when you shine light. 1 electron is going to go to this bromine, and then 1 will go to this bromine. And you'll form 2 radicals. Again, you don't need to show the lone pairs. It's just easier for you to show it like that. But you do need to show the single electron to show that it's a radical.
I was so worried before you added the dots. Before you just drew those dots just now, and I was copying it down. I was like, where did I go?
Yeah, so there's the single electron. The whiteboard? Yeah. Would you rather I write the mechanism on the board?
I'm good. It don't matter to me.
I would just write this part. It wasn't easy to write the dots. Okay, so you end up with 2 radicals, which means they have unpaired electrons. Those unpaired electrons are not happy being unpaired. They want a pair. So they're very energetic. They're going to attack things to get another electron. So we get to this step. Okay, so this single electron from bromine is going to attack this carbon-hydrogen bond on the alkane, okay, which will break this bond. Okay, and this bond has 2 electrons, right? So 1 electron will go between the hydrogen and bromine to form this bond, along with this single electron. Okay, so this electron went to form this bond, and 1 of the electrons from this bond went to form this bond. And the other electron from this carbon-hydrogen bond stayed on the carbon and formed an alkyl radical here. Following me? Okay. So from this step, we formed one of our products, right? It's HBr. It's one of our products. And this mechanism isn't straightforward in the sense that it's step by step, and in the end, you get your products. Okay, it's a cycle. So keep that in mind as you're writing this. Try not to confuse yourself, because these 2 steps will cycle back and forth. Okay, so now that I have my alkyl radical, again, it has a single electron. It's unpaired. It's not happy. It wants to have a pair. So it's going to attack another molecule of bromine from up here. And keep in mind this step, this initiation step here, Those dots are so confusing. I'm so sorry. It's just like a whole mess of dots. Anyway, so when you shine light to break this bond apart, it's not going to break apart every molecule of halogen that you have. Okay, this will only happen to a very small extent. Because when you think about it, you only need this to happen once, right? Because you only need it to happen once to initiate. And then here, you're going to reform that radical, and then these two steps can cycle back and forth without this. Okay, so when you shine light, this does not break apart all of your halogen. So you still have molecular halogen together. Okay, does that make sense?
So are these bromines radicals? Those at the bottom?
These, no. They're molecular bromine. It's just, yeah. So this is just the one with the bond, 3 lone pairs of electrons each. There's no unpaired electrons. Okay, so this alkyl radical is what's doing the attacking in this step. Okay, and this just came from the beginning, from the leftover bromine that didn't get broke apart from the light. Following me? Okay. So this alkyl radical is going to attack this bromine to bromine bond. Okay, break the bond. There's 2 electrons in this bond. So 1 is going to go to form a carbon bromine bond along with that single electron on that carbon. Okay. And then the other electron from this bond is going to reform a bromine radical here. Okay. So 1 electron here formed this bond along with this electron here, which formed this bond, and then the other electron from this bond came and reformed a radical. Okay. And then we formed our other product in this step. So now, these 2 steps together are called propagation. And these 2 steps are going to cycle until you run out or until you do something to stop the reaction. Okay? Any questions? Did I lose anyone?
Why can't we just do it all in one step? Because can the reaction just, like, can one part of the reaction happen and the other not? Like if you run out, is that why we do 2 steps, or?
What do you mean? Like,
I don't.
so you make one product in each step.
Yeah.
Right, so you need both steps to make both products. Does that make sense?
Okay.
I'm sensing that didn't make sense. Would you like to elaborate further?
No, I get it.
You good?
Yeah.
Okay. Any other questions? Okay.
Oh, actually,
Yes.
so is it always only gonna have like 2 steps?
Yeah, so you'll always have initiation and then these 2 steps.
Okay, so you wouldn't have like an extra step for certain, you know, like.
No, not for this reaction. So yeah, it'll always follow this form, break apart the halogen, make the radical, attack the other thing, make another radical, attack the other thing. Make sense?
Yeah.
Okay. So I have another example of this. Try to iron this out a little bit for you guys. Okay. So I know we just barely talked about regiochemistry today, and I'll talk about this more next study session, and we'll also go over it more in class. But, okay, just from looking at this, does anyone know what my major product should be? So, again, I'll go over this more later, and we'll go over it in class. But remember the tertiary secondary radical thing? So if the chlorine goes on the second one, I have a secondary radical, which is more stable than if it went on one on the end, which would be a primary radical. Remember that vaguely? Again, we'll go over that more. So those are my products. Okay, this would be my major product. And then I would also form this as just a minor product. So you should know a question you'd probably be asked is like, go over or write down all the possible products and then write the mechanism for the major product or something to that effect. So just be sure you know how to do that. I'm going to write out the mechanism for this major product here. I'm going to erase this just to make more room. Okay, so my first step is initiation. That's not how you spell initiation. That's okay. Okay, so your first step in these reactions is always going to be to break apart this halogen, okay? So I have, I'll do smaller. So I have Cl to Cl. When I shine light or heat up, it's going to break that bond. Okay, and remember, you're using half arrows to show single electrons. Okay, so one electron will go to that chlorine and one to that chlorine. This bond has 2 electrons. So I end up with 2 chlorine radicals. So now I can move forward. Reaction. It's so hard to spell and talk at the same time. I don't know if I'm spelling anything right. Okay, so now that I have this chlorine radical, now it's going to attack my alkane. Okay, and when you do these mechanisms, you're going to want to show the CH bond that is breaking, just so you can show where your electrons are going. Okay, but this is just the same as this. I just emphasize that CH bond here. Okay, so this chlorine radical is going to attack this CH bond. This CH bond will break. One of these electrons will go between the hydrogen and chlorine to form a hydrogen and chlorine bond, and then the other electron from this CH bond will stay on the carbon and form an alkyl radical. Okay, so here is my first product, and here is an alkyl radical. Everyone following me so far? And this radical, this unpaired electron, is on this carbon, which is connected to 2 other carbons, so this would be a secondary radical. Okay, so my next step is this radical is going to attack another molecule of molecular chlorine. Okay, so when it does that, that chlorine to chlorine bond breaks. Okay, so this single electron goes between here to form a carbon chlorine bond. This chlorine to chlorine bond breaks. One of those electrons also goes in between here to make the carbon chlorine bond, because I need 2 electrons to form a bond. Okay, and this other electron from this bond will go to reform chlorine radical there. Okay, and this is my second product, and then I reformed this radical, which can then go back to this step, attack another molecule, alkane, and then these 2 steps just cycle until you run out or until you stop. Any questions?
I don't really get it.
You get it? Good. Okay. Did I lose anyone?
I'm a little lost, but like, I don't understand the whole major and minor things.
Yeah, well, we just barely touched on that in class. We will go over that a lot more.
So that's not major and minor, it's like even.
This, okay. So major and minor refers to your organic product, which is this. This is a byproduct, so you're not going to call that a major and minor product because we don't really care about this. This is the product we care about. So when you say major and minor, it's only in reference to the big product, the organic product. This is just a byproduct. Does that make sense?
Yeah.
But yeah, we'll go over that more in class. Any other questions? Would you like me to go over another one? Okay, I'll make up another one. Let's see here. Ew. What's happening? I don't want to see my face that big, please. Okay. Let's see. I'm going to do another line structure one. Okay, so say we have something like this. I'm going to ignore the major and minor product thing for now because I don't want to confuse you because we just barely touched on that. So I'm just going to tell you what the major product would be. Okay, so these would be our products, right? One of the hydrogens on this ring got replaced with a bromine, and then the other bromine combined with that hydrogen to form HBr. Okay, so this is just a byproduct. This is the product we actually care about. Okay, so you're always going to start with the initiation step again, which is where we're going to break apart the halogen. And we do this with light or heat. I normally just write light because it's less letters, but you can do either. When you shine light, this bromine to bromine bond is going to break. That bond has 2 electrons. So one will go to this bromine, one will go to that one. And you'll end up with 2 radicals. So now, onto propagation. After I made that initial radical, so now this radical, or these radicals, can attack the alkane. Okay, and again, when you write these mechanisms, you always want to emphasize that CH bond. This is still the same as this. Okay, that CH bond was still there. We just didn't write it then because it's a line structure. But when you're writing the mechanism, you need to emphasize that that bond is there because you're going to do things with the bond. Am I losing anybody there? Does that make sense? Okay. So now this bromine radical is going to attack that CH bond on the ring, which will break that bond. 1 electron from the bond will go in between the hydrogen and bromine to form an HBr bond, along with that single unpaired electron from the radical. And then that other electron from the CH bond, because it had 2 electrons, will stay on the carbon to form an alkyl radical.
Is there like 2 bonds right there because there's 2 H's?
So this is a methyl group. I should have said that. That's my bad.
Yeah.
This would be a methyl group right there. So that's a carbon. that make sense? So yeah, so you're just attacking one CH bond. Okay, so now I formed a product, or one of my products, and then I also formed an alkyl radical. Okay, and this unpaired electron is on this carbon, which is connected to 3 other carbons. So this is a tertiary radical. Okay, so now that I have my alkyl radical, I can form my other product by attacking, I don't have chlorine here. My bad. Okay, so this alkyl radical is going to attack another molecule of bromine, because remember, not all of these molecules broke apart. So I still have a good amount of bromine to bromine. Okay, so that unpaired electron will attack this bond. That bond has 2 electrons. So one of those electrons, after the bond is broken, will go in between here to form a carbon-bromine bond, along with that single electron on the carbon. And then that other electron from the Br to Br bond will go to the other bromine to reform a radical. Okay. So now this radical can go on to attack another alkane molecule, and those 2 steps will cycle. So this and this are my 2 products. Any questions? Mm-hmm.
So for where you put the bromine, that has to do with the major and minor, right? Like
Mm-hmm.
being like a tertiary.
Mm-hmm. Yeah, so the major product will depend on the stability of the intermediate radical. So if the intermediate would be a tertiary radical, it would be more stable than if it were a secondary radical primary. So that's the basis on the major and minor products. Any other questions? Alrighty, my friends. Well, that's all I got. I can answer any questions you have about homework if you want to hang back. If not, you're free to go.